But the real key idea that I want us to get across is the idea of a function. A function turns out to be a mathematical idea that has applications all over the place. So this is a central mathematical idea, and we want to get familiar and fluent with it. So what is a function? A function is a particular kind of relation, and it has the property that for every x value in your domain, there's only one y value in the range. Now, the reason that we only want one y value is these functions are used to model a whole lot of things. And so models are used to predict what's going to happen. And if you're going to predict what happens, you only want one output. That's your prediction. If you've got more than one output, well, you can't tell which one's going to happen. So mathematicians and engineers and scientists have concentrated on those models where there's just one value. If there's more than one value, there's lots of stuff, then you've got to go and do statistics instead. Okay, and of course there's a whole theory of statistics that you can do as well. Okay, so that's basically why we're really interested in functions and why this exactly one value bit is important. So let me say, look, this whole box here is an important thing. The idea of a function. So clearly, this relation we had here, x squared plus y squared equal to 1, is not a function because we saw before that x equal to a half is in the domain, but a half the square root of 3 on 2 and a half minus the square root of 3 are in the relation. So in that case, a half is related to root 3 on 2 and to minus root 3 on 2, and that's not what we want here. We only want one possible value for y. Whereas in this particular relation, no matter which x value I choose, I only ever have one y value associated with it. So this one is a function for every x in the domain. There is only one y value associated with it. So that's our key idea. And of course, if you have the graph of the relation, you can tell straight away whether the thing's got a graph of a functional relation, because if I choose any value of x and draw a vertical line, if it's a function, it'll only ever cut that graph once. That's the y value associated with it. So you can see any vertical line here will cut the graph once, whereas if I go to my circle one here, you can see a vertical line, for example, here, cuts the graph more than once. So therefore that's a relation, that one's a function. They're both relations. This one's a function, this one's not. It's probably the way to say it. And that little observation is called the vertical line test. A relation is a function if each vertical line intersects its graph at most once. So let's highlight that as being important as well. And so down here I've got a number of graphs. It says which of the following graphs are associated with a function. So this graph here, I start drawing vertical lines and I can see, let me just draw that one for example. But it doesn't matter which one that I draw, it cuts the graph just once, so therefore this one is definitely the graph of a function or something that I can interpret as a function. Whereas for this set of ordered pairs over here on the right, if I draw a vertical line here, we can see that it cuts the graph more than once, and so this one is not a function. When we get to the second half of this course and we start talking about calculus, all of the techniques that you have in calculus only apply to functions. Okay, so it's important that we can recognise them. So I've got a few more examples here. And the ones on the left, either of these ones, doesn't matter which vertical line I draw, they only ever cut the graph once. So this side are functions, that one and that one, whereas these ones over here, even though here the vertical line cuts it once, there is a vertical line that cuts it more than once. So for example, if I were to draw that vertical line, that cuts the graph more than once, so that precludes that from being a function. Likewise here. That's not even vertical, but anyway. Okay, so these not functions. Now, in terms of notation, when we have a relation and we've decided that it's a function, quite often we refer to the y value, rather than just writing the y value, we write it actually as f of x, is how we say that. That is the same as y. They're interchangeable. So even though it's got f of x, it still represents just a number. The number that it represents is the value of your relationship at that particular value of x. So this notation here is supposed to remind you that the y value will depend upon the x value that you've chosen. But that whole thing still represents just a number. So what that means is that you can do algebra with it. Right? This is just a number, so therefore I can add two numbers together and so forth. So all the techniques of algebra that you have, you can actually do using f of x as your symbol. That can get confusing, but hopefully not so. If you remember, that just represents a number. So what you can do with it is what you can do with your arithmetic. As long as you know your laws of arithmetic, you'll be right. So for example, if I had this particular, well, A, we decided it was a relation, then we decided it was a function, so I could rewrite that, I could define that function by writing this. F of x is 2 minus x. That function and that function are the same thing, just two different ways of writing the same thing. And what I could do is I could say, look, that now, that symbol, F1, is the y value when x is equal to 1. And as you can see, when x is equal to 1, that's 2 minus 1. So f of 1 is equal to 1, is how we would interpret that number there. And of course that says x equal to 1 is related to y equal to 1. Or to be more specific, I can say, no, I might leave it at that for the minute. I could say f of minus 1, that would be 2 minus 1, so that would be 3. So I say f of minus 1 is 3. That means, I can interpret that minus 1, 3 is on the graph. That's another interpretation. It's on the graph of this function. So we're bombarding you with a whole lot of new terminology and notation here. But we're going to use this notation will be used in every subsequent, or for the rest of this course and through every other maths course that you'll be doing. So it's good that we can, if we can get our head around it. The other thing that's interesting to note here is, imagine that I didn't have the graph of that. I could still tell that it's a function, because if I chose an x value, 2 minus x, there's only one possibility for that. So when I put in an x value, I'm only going to get one value associated with it. Whereas, if I was back with this one here, x squared plus y squared equal to 1, if I chose x equal to 1, I would have here 1 plus, oh, what a bad choice. I want to put x equal to a half in there, just make it better for me. So here we go. I'll do it over this side, make it a bit bigger. So I have here x squared plus y squared is equal to 1. That would give me a half squared plus y squared is equal to 1. Y squared is equal to 1 minus a quarter, 3/4. You can see here I can produce two different y values, because the square root is plus or minus in there. So I can tell algebraically that this thing isn't a function. For every value of x that I choose, there can only be one value of y for the relationship to be a function. When you get into later maths classes, you'll find the definition of function is quite broad. I'm going to try and give a formal definition here of a function that suits what we're going to talk about in this class. I might put that there. So for us, a function is a rule that we shall call f that assigns to each element x in a set, that's called the domain, exactly one element, which is f of x, on a different set. And these sets here are numbers, sets of real numbers for us. And as I say, in this course, a and b are real numbers. So that's our formal definition of a function. And armed with that, we're now ready to do some serious stuff. So this says, sketch the graph of this particular function and state its domain and range. That's the kind of task that you'll be asked to do. So, first of all, is it obvious that this thing's a function? Well, if I choose a value of x, let me choose x equal to 1, then x squared is definitely well defined. 1 squared is 1. 9 minus 1 gives me 8. There's only one possible value. And that will happen no matter what x value I choose. So, yep, I reckon this is indeed a function. So no problems there. So the fact that I've got an x squared isn't a problem. The problem over here was the y squared. That was the thing that gave us grief over here. Okay. Now the other thing is, this here is a graph. And remember, I could just have, I might do this on a separate sheet actually. remember that f of x is just the same thing as y. So I could write this as y is equal to 9 minus x squared. That equation is definitely an equation in two variables, but it's not linear because there's a squared term in here. And this was one of those places where I thought to myself, hang on, we haven't talked to you about what happens when you haven't got a linear equation. So I think I better just quickly give you an idea. So this here is called obviously a quadratic equation in here, because we've got a quadratic. On the right-hand side here, I have a quadratic trinomial, if you like. And so down here, I've just said a little as an aside. The graph associated with a quadratic equation of two variables of this particular form, y is equal to ax squared plus bx plus c, is a parabola. And I'm just hoping that you know what a parabola is. Okay, an example of a parabola I've got here, and I'll draw some more in a minute. When you're up, here it is. This is the graph. This is what a parabola looks like. So I've said if the coefficient of x squared is positive, then your parabola is like that one there. It's called concave up. Whereas if the coefficient of the x squared is negative, your parabola is concave down. So let's do some examples of that. So in here, if I have y is equal to ax squared plus bx plus c, and a is positive, let's call that x, let's call that y, then the graph will look something like this, perhaps. And when x is 0, y is equal to c, so my y-intercept is the value of c. Where this cuts the graph is where y is equal to 0, so that is where ax squared plus bx plus c is equal to 0. They are the x-intercepts. And you know how to solve that sort of equation. So you can find the x-intercepts and you can find the y-intercept. The other thing that you probably need to know here to give you a good picture is that the vertex here, the x value of that is negative b on 2a. That's that x value there. And armed with that, you should be able to sketch all of your quadratic type equations. Let me do the same thing when a is less than 0. So let me slide that up to there. And now let me say I have y is equal to ax squared plus bx plus c, but a is less than 0. X, y. So this time it's concave down. So I should have said that's concave up. This one is concave down. Where it cuts the axis is again c, whatever value of c is. Where it cuts the x-axis, that's where ax squared plus bx plus c is equal to 0. They're my x-intercepts. And again, the vertex, the x value of the vertex is x is equal to negative b on 2a. So there are your two possibilities for your parabolas.
When you say vertex, you just mean the highest point or the lowest point?
That's correct. The point where it turns over, yes. So I'm hoping, armed with that you can now do all the questions that appear in the notes and in the exercises. And in particular, I hope we can do this one here. This 9 minus x squared, I would actually write that as minus x squared plus no x's plus 9. So a is equal to minus 1, b is equal to 0, c is equal to 9. So this is going to be a concave down parabola. Negative b on 2a, so I'm going to have 0 on 2a. Its vertex is going to be on the y-axis, and it cuts the y-axis at 9 in there. So let me put all that up there, and we'll actually draw a picture of this one. So. Sorry?
Does your no x's in that case come from changing to f of x?
No, no, no. The f of x turned into y. Right? Okay. The fact that it's no x is because there's no x. Okay? Yeah. So in here it says, draw the graph of this particular function, but only draw it for x values between -4 and 4, is what that says there. So I'm going from, just there to there. They're the x values that I'm going to use. Now, in this case, here I've got c is equal to 9 in here, so I know, let's change this scale. Well, let me make that 2, 4, 6, 8, and then 9 sits nicely there for me, okay? So I can actually fit it on the picture. So that will be 9 there. That's where it cuts the y-axis. Now, the vertex, the x value of the vertex is negative b on 2a. And in this case, that was 0 on -2, so that's 0. So in fact, that point is the vertex in this case. So when x is 0, we can see y is 9. So that tells me that 0, 9 is the vertex. It goes that way around, it's concave down, it turns around at 0, 9. The other thing I'd like to know is where it cuts the x-axis. So where is 9 minus x squared equal to 0? In this case, that was the very easiest quadratic trinomial we could solve, because I could just make x the subject of that, and I get x squared is equal to 9, so x is equal to plus or minus the square root of 9, which is plus or minus 3. So here it cuts the axis there and there. Now when x is equal to 4, I've got 9 minus 16, way down. So anyway, it'll go like this. So it comes, whoops, that's not a very good parabola. Like this. Down here, comes down here, like that. And I can say when x is equal to 4, y is equal to 9 minus 4 squared, that's minus 7. So way down here, this thing here is 4 minus 7, down there. That's the world's wonkiest parabola, but you get the drift. That would be the graph of y is equal to 9 minus x squared. The C. Yep.
Is that always the y-intercept?
Yes. Yeah, because it's the y value when x is 0, and when x is 0, a times 0 squared is 0, b times 0 is 0, so y will be equal to c if I put it in here. Yeah. Okay, when I put x equal to 0 there, I get y is equal to c. Okay, so c is always the y-intercept. Yep. Okay, so armed with that graph, well, it told me to sketch the graph, so I did that. But I can also now see the domain and the range in here. So, well, in this case, they said sketch the graph for x values between -4 and 4. So that's my domain. They're the x values that we've chosen. Now, interestingly here, this has got a just less than rather than less than or equal to. And so what we would do down here is we would actually put an open circle on our graph to say the graph goes up to that point but doesn't actually include that point in there. So our domain, in this case, it's given to us already. We didn't have to work that out. It's the set of x values such that x is between -4 and +4. The range, however, is the set of y values such that, now what y value do we get? Well, clearly when I started at minus 4, I started at y was equal to minus 7. As x moved across, y moved all the way up to 9, and then as I came across here, y went back down to minus 7. So the y values that I actually see in my relationship always go between minus 7 and plus 9. So this will be minus 7 is less than y is less than or equal to 9. So minus 7's not in it, plus 9 is in it. Because there is a y value of 9, there is a point with a y value of 9, there's not a point with a y value of minus 7 because of our open circles. And so that's our range. So here's another example of a function. It says sketch the graph of this particular function. And once again, if I pick a value for x, just say I pick x is equal to 1, then x squared is 1, 4 minus 1 is 3. I can take the positive square root. That symbol there means take the positive square root. Then it says multiply by minus 1. So when I do that, I get a unique value here. So therefore, this is indeed a function. The other thing is sometimes we want more than one function, so we've got to have names other than f. So A, B, C, F, G, yeah, G and H are just call them whatever you like, okay? We don't have to use f as the name of the function, but you can see that is function notation. The value of h depends on x is what that's trying to tell us, but that just represents a number. So in here it says state the largest possible domain for this function and find the corresponding range. So what it's saying is, for what values of x can I actually work out h? And in this case, we know that when you take the square root, you can only do that for a positive or a non-negative number because you'll find the square root of 0. So what happens in here is we have to choose an x such that this 4 minus x squared is positive. So I can say in here, the domain, the largest possible domain, will be the set of x values such that 4 minus x squared is greater than or equal to 0. Now I'm going to ask you to use common sense here. I don't know if that's a wise idea, but anyway, let's do that. You can see that if I put x equal to 1, that works. If I put x equal to 2, 2 squared is 4. But you can see that once I get to 3, 3 squared is too big. And in fact, anything bigger than 2 is not going to work. It's going to make that negative. And likewise, because it's a squared, anything smaller than minus 2. For example, if I put minus 3 in here, minus 3 squared is 9, 4 minus 9 is negative. And so I can't take the square root of that. So the set of x values that make 4 minus x squared positive is in fact the set of x values between minus 2 and 2. If you wanted to in here, you could have actually drawn the graph of this thing and had a look where the graph is above the axis. But for the minute, I'm just going to leave it at that. So we can find the domain. How do we find the range? Well, to me, the best way of finding the range, the easiest way is actually to sketch the graph of the thing. I can't give you a method that will always find you the range. So in here, I'll just say, let's have a look at the graph. And so to look at the graph, it asks us to sketch the graph anyway, so we needed to do this. So the graph can be found from, now in here, instead of having h of x, I'm just going to put y. I'm going to say y is equal to minus the square root of 4 minus x squared. And in this case, that doesn't look like anything much. But if I square both sides, I square both sides. Then on the left-hand side, I get y squared. And on the right-hand side, I have this multiplied by itself. The negative times the negative gives a positive. The square roots undo each other, and so I'm left here with 4 minus x squared. Do you believe me? More to the point, could you do that yourself? Anyway, if I rearrange that, that now becomes x squared plus y squared is equal to 4. Okay, told you it was going to come up. That we recognise. That is in fact a circle with centre 0, 0 and radius 2. So the graph of that looks something like this. I'm not very good at drawing circles, and I'm just dotting it in for the minute. So that's the graph of x squared plus y squared is equal to 4. But remember, if I go backwards in what I've done here, I've got x squared plus y squared is equal to 4, so therefore y squared is equal to 4 minus x squared. But in here, when I've taken the square root, I've only taken the negative answer. I haven't taken the positive answer. Right? There's two possible square roots. This one says take the negative one, so in fact, I've only am going to get the points down the bottom here. Just that one, those ones down there. And as a result, given that my graph is just the filled in one, that actually passes the vertical line test. Because the dotted part up the top I haven't used. Right? That's not in the graph. So this thing here is the graph of hx is equal to minus the square root of 4 minus x squared. Just the bottom half of the circle. So this is a circle, centre 0, 0 and radius 2 in here. This is the lower semicircle. In there. And now, given that I've managed to recognise that graph, I can now work out the range. As x goes between minus 2 and plus 2, we can see y starts at 0, goes down to minus 2, and then goes back up to 0. So the range will be the set of y values such that y goes between minus 2 and 0. So you could think to yourself when you're doing a range, if I've got my ruler, where'd my ruler go? Here it is. If I have a horizontal line, it's those values of y where a horizontal line cuts the axis, cuts the graph, I should say. So up here, there's no graph, so those y values aren't in the range. But as soon as I come down here, the horizontal line cuts the axis, cuts the axis, cuts the axis. So all of those points are in the range. But down here, there's no graph, so those y values aren't in the range. So you can think of the range by looking at the horizontal line. As you can see, these questions here assume that you know a fair bit of coordinate geometry already. I imagine that when I set assessment tasks, I won't make that same assumption. Okay? If I do, you can come and lynch me. You'll probably do that anyway, but we'll see how we go. So here's another one. It says, find the largest possible domain of this function and make a sketch. So again, this is at the hard end of the scale. The first part's not. The domain is fine. The domain says, for what values of x can I actually calculate a value for f? And in here, I can calculate f so long as the denominator is not 0, because I can't divide by 0. That's an undefined operation. So my domain in here will be the set of x values such that the denominator is not 0. Denominator is not 0. So that means it's the set of x values such that x minus 2 is not equal to 0. And of course, that is the set of x values such that x is not equal to 2. So long as x is not 2, I can calculate the value of f. When x is equal to 2, the thing is undefined. So x equal to 2 is not in the domain. So that means when I come down here and sketch the graph of this thing, I can fit that in, there's no point on the graph associated with x equal to 2. So I'm going to actually draw a dotted line in here. Because what this means is x equal to 2, I'm going to use big words on you here, is a vertical asymptote. So that's the graph of the line x is equal to 2. So let me explain. An asymptote is a line that the graph gets very close to but never reaches. That's what we mean by asymptote. Now, how do I know that? Have a look here. As x gets closer and closer to 2, like 2.5, then 2 1/4, 2 1/8, and so forth, x minus 2 gets closer and closer to 0. And as I divide by smaller and smaller numbers, like 1 divided by a half is 2, 1 divided by a third is 3, 1 divided by a tenth is 10, you can see the function is getting bigger and bigger and bigger. Right? So as x gets close to 2, f gets larger and larger. So mathematically I would write that as, I would say, as x gets closer to 2, that's what that symbol there means. And I'm going to make it even look more complicated because I'm going to put a plus there. As x gets closer to 2 from numbers bigger than 2, so I'll start at 2 1/2, then 2 1/4, 2 1/3, f goes towards infinity. F gets larger, the y value gets larger. So this graph goes up like that. It gets closer and closer and closer to this thing, but it never actually reaches it. That's what happens there. However, if I come towards 2, but from values a little bit smaller, like, for example, if I put in 1 1/2, 1 1/2 minus 2 is minus a half. 1 divided minus a half is minus 2. And so what happens on this side is, yes, the number's getting bigger, but it's getting bigger negatively. The denominator is always negative, so the y value is always negative. So as x goes towards 2 from the left-hand side, f goes towards minus infinity, and this graph goes down there like that. So again, whoops, slide that up a bit. Again, it's getting closer and closer to x equal to 2, but it never actually reaches it. And that's what we mean by a vertical asymptote. In there. So I found the domain, that was good, right? There it is. Set of x values not equal to 2. So this part here, the difficult part here is, what does that mean, sketching its graph? What else can I do in here to try and get an idea of what this graph looks like? Well, I can certainly find the y-intercept because I can put x equal to 0. So I can say when x is equal to 0, f is equal to 1 over 0 minus 2, that's minus a half. So I know it goes through that point there. So I've got some idea of what the graph does. I can get even more of an idea and by thinking of this, and I can now say, what happens when x gets very, very large, as x goes towards infinity? So go back to our formula. If this was 100, then 1 on 98, that's fairly small. If this was 1,000, 1 on 998, even smaller. So as x gets larger and larger and larger, this thing gets closer and closer to 0. You can think of it as 1 on 1,000, 1 on 1,000,000, 1 on 5,000,000. So as we go out here, f goes towards 0, and I can put a little plus sign because those numbers are always positive. So it's going towards 0 from above. So I can say the graph does that. There's a lot of thinking in here. This will take some practice. Yeah, that's all I can say. And the last thing that I'm going to look at in this case is what happens as x goes towards minus infinity. So as I choose x values out here, instead of being, like if I choose minus 1,000, then this is 1 over minus 1,002. So again, it's very small, but it is negative. So f goes towards 0, but it's on the negative side. So it actually comes across like that. And so now I'm going to take a leap of faith, and I'm going to join those up. How do I know those join up? I don't. Eventually, when you do some calculus, we can show that joining those up is the right thing to do. But for the minute, I'm just going to say, that's what I think happens. So there is my graph of 1 over x minus 2. That is harder than what I'm going to get you to do in any assessment task, initially. We're going to come back and do some more of this later. The other thing interesting here is notice how this graph, it gets closer and closer to 0 on that side and closer to 0 there. So this is also an asymptote. So in fact, the line y equal to 0 is a horizontal asymptote. So they're big words that as we use them more often, hopefully you'll get used to them. Big words and lots of symbols in there as well. But as I say, if I keep using them, hopefully we'll get familiar with them. I would say at this stage, don't be too despairing if you don't get this first go. Okay, don't panic yet. We're going to come back and have a look at this stuff again. Then panic, okay? Don't panic yet.